Here in chapter 6, we first talked about a portfolio, the function and goal for the portfolio. We're trying to construct a phasing portfolio. To construct a phasing portfolio, we need to do a one-job-based diversification. As we add more stocks into our portfolio, we know that the overall risk of our portfolio goes down. We have this kind of relationship between number of assets in our portfolio and the risk of our portfolio. Next, we looked at there are two sources of risk for our portfolio. One is systematic risk, another is non-systematic risk. Below our plot, this part is a systematic risk. You couldn't diversify systematic risk. It's non-diversifiable, so you can't eliminate this part. It always exists. But for the non-systematic risk, we also call it a firm-specific risk. You can actually eliminate this part by adding more stocks into your portfolio. So this part, you can reduce the risk, but this part, you can't change it. Then we looked at the asset allocation with two risky assets. So when we talk about the asset allocation of two risky assets, we first looked at a scenario analysis. As we talked in chapter 5, we can have, like, for example, 4 scenarios. Under each scenarios, we have a specific probability of each scenarios. Then in chapter 5, we looked at how to calculate the expected return of scenario analysis. We use the probability times the return under each scenario. Then we add all the numbers together. The result is expected return. Here we got 10% in chapter 5. Here in chapter 6, we add another line for bonds. So we do the same thing, probability times return, then add them together. The result is the expected return of bond, which is 5%. So the expected return of the portfolio, for example, this information is given that the weight in the stock equal to 40%, the weight in the bond equal to 60%. So we can use this equation 40 times 10% plus 60 times 5% to calculate the expected return of the portfolio. Then covariance is covariance measures the co-movement of stock and bonds. So in this equation, you can notice that there's no weights. Like for the expected return here, you have weights of stock, weights of bonds. But in this equation, there's no weights. It's just simply a statistical measurement of the co-movement of two assets. So you use probability on each scenario times the return deviate from the expected return. Use stock times the bond times the probability. Adding them together, you get a negative 74.8% covariance for the stock and bonds here. So it's hard to compare different portfolio with different covariance because different assets have different variance. It's hard to measure that. So we need to standardize our covariance by divide covariance by the standard deviation of stock and bonds. So the equation for the correlation is covariance divided by standard deviation of stock and standard deviation of bonds. So for the correlation is a number between -1 and 1, which is standardized. We can easily use this number to represent the correlationship between two assets, and this will give us either way to describe it. For example, here we have 3 special cases. One is no correlation, one is perfect correlation, one is perfect negative correlation. So for no correlation, we know one stock price movement not affect the other one keep the same movement. So they literally not move together, so they have no correlations, where we can simplify the equation for the variance. We put 0 here, so it eliminates the third term. We only have the previous part. For the perfect correlation, the two stocks literally moving together with the same magnitude. So when the stock goes down, other stock goes down by the same percentage. So they are perfect sync each other. You can treat these two as one stock. So here after you simplify the variance equation, it's actually the standard deviation, actually the sum of the weights times the standard deviation of each stock. You can treat them as one because they move exactly the same. Another we have the perfect negative correlation, that one stock move up, the other stock move exactly the opposite. We can put -1 in the third term of our variance equation. So the standard deviation of the whole thing become weight of stock times standard deviation of stock subtract weight of bond times the standard deviation of bonds. So because they simply substitute each other, so you can simply subtract one from another. Otherwise, you have to use the whole equation to calculate the variance of this portfolio. So here next, let's talk about opportunity set. For the opportunity set, you literally can find all the combinations of your two assets on this opportunity set. For example, in this point, you have 0% in stock, 100% in bond. You can use equation from previous page to calculate expected return and standard deviation. That this will give you two numbers. You can plot it on the opportunity set. For each combination, you can find exactly a point on this opportunity set. So we can write different percentage in stock and one subtract percentage in stock to calculate the percentage in bond, then find all the portfolio's expected return and portfolio's standard deviation, then find other point on a relationship between return and the standard deviation plot, the overall points construct this curve. We call it opportunity set. So for stock and bond, for two assets with different correlation, we actually draw the opportunity set a little differently. Here, for example, if the two stocks perfectly sync each other, we think they have a rho equal to 1, correlation equal to 1. It's actually just treat them as one stock. We have this straight line as our opportunity set. For standard deviation equal -1, we can just simply treat them as two individual assets that go into a different direction. We can plot it like this way. Then for for the correlation equal to 0, it's the curve we plot either here. So note that in chapter 5, we talk about risky asset and risk-free asset. We know that the risk-free asset, the return of risk-free asset not move with the risky asset. So the movement of risky asset and risk-free asset are totally uncorrelated, but they don't have a correlation equal to 0. Why? Because if you look at our equation of correlation, you can see that the standard deviation of the risk-free asset equal to 0. So this term is non-defined. We can't say this equal to 0. So we actually couldn't plot it as opportunity set here for correlation equal to 0. What we can do is a capital allocation line we did earlier. We find our portfolio and connect it with the risk-free point. That's actually the capital allocation line we talked in chapter 5. It's actually the opportunity set for the portfolio with risky asset and risk-free asset, but we don't necessarily call it opportunity set. We call it the capital allocation line there. For the opportunity set we talk about here, we only include two risky assets, not risk-free asset, because we don't know the correlationship between risky asset and risk-free asset. So here, with a different level of correlation, we can find if rho equal to 0.5, the opportunity set is in between 0 and 1. The negative 0.5 is a plot in between 0 and -1. That way we can draw a different opportunity set. Then now here we want to find among all those portfolios, we want to find the portfolio with the smallest, the minimal variance. How to do that? We write this equation. We change the weight of stock to 1 subtract weight of bond, where we know the standard deviation of the bond and stock. We also know the covariance between stock and bond. The only thing we don't know is the weight of bond. So we differentiate this equation by weight of bond. We can solve this to get the weight of bond that give us minimal variance the portfolio with minimal variance, where the weight of stock is 1 subtract weight of bonds. Then we can find the 2 points of the 2% of the stock and bond. Then we can find the expected return of the portfolio and the standard deviation of the portfolio. Then we can find this minimal variance portfolio point. Here is a simplified example for minimal variance point. For example, we have stock and bond. We have 2 stock A and B with different expected return and different level of standard deviation. Suppose they have 0 correlation. That's simplified our equation. We suppose the proportion in stock B is P. Then we're trying to find the minimal variance point. The P give us a minimal variance. We can write the equation, the last term equal to 0, so we drop that. Then we differentiate this equation by P. This term equal to 0, then we solve this equation. We find that if you have 59% in stock B, 40% in stock A, that give you the point with minimal variance. Then we looked at the efficient frontier and the optimal portfolio. What is efficient frontier? If you look at our opportunity set, the curve above the minimal variance is our efficient frontier. For example, point A and B giving certain level of risk. The point A, portfolio A has a larger expected return than the portfolio B, so A is more efficient than B. So we definitely going to choose portfolio A. So for efficient frontier, all the portfolio on it has a highest expected return under certain level of risk. Then, as we talked earlier, we can connect the portfolio and the risk-free points together to construct our capital allocation line. For the opportunities, for the portfolios on the opportunity set, we can find one optimal portfolio that give us the highest slope. When we connect that this portfolio with a risk-free point, we can get a highest slope, which means the highest Sharpe ratio. We know that we always want to find the portfolio with highest Sharpe ratio, because highest Sharpe ratio meaning lower standard deviation and a higher expected return. So here you can say we have an example for the optimal capital allocation line and capital allocation line 2, capital allocation line 1. For 1 is impossible because we don't have any portfolio on the capital allocation line. We cannot draw this one. For capital allocation line 2 and the optimal capital allocation line, we know 2 dominated by optimal because the capital allocation line 2 has smaller slope. So for the optimal capital allocation line, always have highest slope, where we also have the highest Sharpe ratio. So how do we find the optimal capital allocation line? We're trying to find the portfolio with highest Sharpe ratio. So we want to find the maximum of Sharpe ratio. We can simply plug our equation of expected return and the standard deviation of the portfolio to the Sharpe ratio equation, then differentiate it by the weight of one of the assets. Then we can get the weight of the optimal portfolio. How to do that, we don't need to know for our class. It generates a super complicated equation. You don't need to include this in your formula sheet, and you also, I won't let you calculate this because this one looks super time consuming to do. Even for the minimal variance portfolio, I won't let you calculate this complicated equation. For the example, it's also kind of complicated because you need to differentiate that. So I also won't let you calculate the one with derivatives. So don't worry about minimum variance and optimal risky portfolio. I do show you how to find the optimal portfolio and the minimal variance portfolio during the class time on Wednesday. We use Excel solver to find the optimal and the minimal variance point. If you want to learn more about that, please email me. Then I want to talk about efficient frontier with many assets. Here, for example, we have stock A and B. We can construct the opportunity set. Above that is our efficient frontier. We can find our optimal on it. Suppose we have another stock C above it. We can connect the optimal one and C to find another optimal here. If we have a C below our efficient frontier, we probably don't want to include include the stock C because it's already dominated by our efficient frontier. So the only case we want to include it is this point above or to the left of our efficient frontier. So after we connect the first optimal point and the stock C, we can find another new optimal point. Suppose we have another point to the left to our efficient frontier. We can connect that to get a new efficient frontier. So after we combine multiple assets into our portfolio, our efficient frontier move to the northwest. To move to this direction, you need to know that the opportunity set always move to the northwest. Then we talk about the single index stock market. It's a in this single index stock market model, we have RI, which is a return of an individual stock. The beta is the sensitivity of an individual stock to the market. The alpha here is a return of stock generated independent to the market. And E is an arrow term, where we kind of looked at a individual stock's return during class and the market return. Then we find all the points on a plot. Then we can find the linear relationship between stock and market. We looked at the regression table during class. You need to know which one is alpha, which one is beta. So here in this model, it shows us that the relationship of an individual stock and overall market return. So this plot would be on a relationship of individual stock and market, and it's a linear relationship between two returns. For the variance of the individual stock, we can put the whole equation to the variance equation here. The alpha is a constant we get on our regression tables. So for the variance of a constant, it always equal to 0. So we drop the alpha here. For the beta times market return, the beta also a constant we trying to find from the regression table. So it's also a constant. For the variance of a constant times a risk of the market, we can move out the constant and square it. Then we keep the variance of our market return. The last term is an error term. It also is always different. It's not a constant. So the variance of the error term, we keep it here. So this residual risk, we call it firm-specific risk. That's unique for each individual stocks. But for the first part, the square of beta times the variance of market is a systematic risk times the sensitivity to the risk of the market. So this whole part is our systematic risk. When we add these two together, systematic risk plus firm-specific risk, we can find that's our total risk for these individual stocks. So here the beta and the return of the market term, the variance of that captures systematic risk. The variance of error term captures the firm-specific risk. For the alpha, it is a return the stock generates independent of the market. If it's larger than 0, it outperforms the market. If smaller than 0, it underperform to the market. It, it depends on the characteristic of that individual stock. For the beta is a sensitivity to the systematic risk. So the systematic risk is a variance of the market. For the beta is a covariance of the individual stock and the market over the variance of the market. If it is equal to 0, if it is equal to 1, it means this individual stock perfectly sync the market. If larger than 1, means it's more volatile than the market. If smaller than 1, it means the stock is less volatile than the market. Next, let's look at the security characteristic line. For the security characteristic line, you need to understand this plot. Here it shows if it above the 0 point, meaning that it has a large alpha larger than 0, meaning this individual stock outperform have a positive alpha that outperform the market. And beta larger than 0 means the sensitivity of this individual stock is positively correlated to the market. If the slope goes up, means the sensitivity of the market goes up. If the plot more flat, meaning that the sensitivity to the market is smaller. You can see here we have the points near the linear relationship between individual stock and market, meaning that this plot, those points are less scattered, meaning the firm-specific risk is lower here. Here is another example. If the security characteristic line goes to this direction, meaning it's negatively correlated to the market, so it has a negative beta. So when market goes up, this stock goes down, and it's below this 0 point, meaning that the alpha is smaller than 0. This one is more flat than this previous security characteristic line, meaning that it less sensitivity to the stock market shocks. And you can see the points of each returns are more scattered than the one in the previous plot, meaning that the firm-specific risk of this stock is higher than the previous plot. So in this chapter, you need to know how to read those security characteristic line. I think this is pretty much everything about this